So we'll start. Good afternoon, everyone. I'm very happy to welcome our today's speaker, Professor Apoorva Khare from IIC Bangalore. And he will be talking on moments in positivity and will show us connections with various areas, ranging from geometry to statistics. So before starting with the talk, I would like to request you all to keep your audio on mute and unmute yourself only when you want to say something or ask something from the speaker. So now I request Apoorva to start. Welcome, Apoorva.
Thank you. Thank you so much, Tanvi. It's a pleasure to be, virtually, unfortunately at ISI Delhi. I was there last December, I think, for Professor Bapat's birthday conference. And of course, I met some of you then. And it's always a pleasure to be there. But this is a very weird time. So anyway. Oh, no, so not last November, last November. Yes, I forget. Okay, but so without further ado, let me, as Tanvi said, tell you about positivity, moments, and connections to various other things, including metric geometry, statistics, and some combinatorics at the end. Part of this is based on joint works with various people. Part of it is historical. And the idea is I want to, in some sense, capture some snapshots of these connections. So the talk itself is split into 3 or 4 or 5 parts. Each of them is roughly 10 minutes long or 12 minutes long. And together they make up the whole talk. Yeah, so each of them is kind of distinct, disparate from the rest. Okay, so let's start with some definitions and a working example, which I will get to in the style of Chekhov's gun at the very end. So real symmetric, all matrices in this talk will be real and symmetric. Yeah, I think so. So a real symmetric matrix is positive semidefinite if all eigenvalues are non-negative, or equivalently, of course, the name comes from the fact that the quadratic form induced by this matrix is a positive semidefinite. Here are 2 examples. These 5 by 5 correlation matrices. One can check, that they are actually positive semidefinite. In any case, the point is the point is to notice that they have these 0 patterns. So here are 0, 0, zeros. And so if you think of this as a pattern of zeros according to a graph, the idea is that the graph should be on the number of vertices equal to the dimension of the matrix. So it's a 5 by 5. So it's a graph on 5 nodes. And the node 1 is connected to node 2 because this diagonal entry is non-zero, off diagonal. And 3, 4, 5 are 0. So node 1 is not connected to 3, 4, and 5. Similarly, node 2 is connected to node 1 and 3, but not 4 and 5, and so on and so forth. Okay? And then similarly, this one as well. Now, so this is just a path graph, 1 connected to 2, 2 to 3, 3 to 4, 4 to 5. This one is a banded graph. So 1 connected to 2 and 3, 2 to 1, 3, and 4. So basically, every node is connected to 2 nodes before and 2 nodes after, if there exist such nodes, when you write the nodes down on the number line, 1, 2, 3, 4, 5. Okay. And the question that I want to talk about is to raise every entry to the alpha power for some alpha, for which alpha are these resulting matrices positive semidefinite. So if you start with a positive matrix and you raise every entry to some power, then what happens? When does it stay positive? Actually, in fact, variants of this question have sort of been studied by 2 people in the audience, at least here. Okay. So now, so that is the working example, just to set some notation, and I will get back to it at the end. So, okay, good. So see the time. So now let me start with how this question, this kind of area arose in the first place. And then the second part, I'll get to the second part later. So the notion of positivity has been around for quite a long time. It has been studied in, of course, the math literature in many different ways. Some of the flavors, and the first one here is the most prominent for today's talk, is to study the notion of positive matrices. A positive semidefinite matrix is essentially the same thing as a correlation matrix, so as a covariance matrix. And if the diagonal entries are all 1, then that's the same thing as a correlation matrix. But then you also have things like positive semidefinite Toeplitz matrices, or even infinite arrays of Toeplitz matrices, for which every principal submatrix is positive semidefinite. These are corresponding to positive definite sequences or Fourier-Stieltjes coefficients of positive measures on the circle. Similarly, you can talk about positive measures on the real line. So take some kind of a probability distribution, if you will, and look at its moment sequence, right? And now you arrange the moment sequence in a suitable way, the entries, you get a matrix, which is a Hunkel matrix, which is positive semi-definite. And in fact, usually positive definite as well. Then there are things like totally positive matrices or totally positive kernels. Examples include Polya frequency functions and Polya frequency sequences. Hilbert space kernels, positive definite functions on metric spaces or groups. And so there are a lot of different ways that positivity has been studied in literature. And so has the idea of understanding what operations preserve these structures, these positivity structures. And that itself has been studied for a long time. So as I said, the prominent one for today's talk is positive semi-definite matrices. So let Pn of I, so given a domain I in the real line, let Pn of I denote the n by n positive matrices. And this time I want the entries to be in I. So given a function, the question that I'm interested in and have been for a while is to understand when is it that if you start with a matrix A in Pn of I, you end up with a matrix f of Aij, that itself should also be positive semi-definite. Okay? So when does applying a function entry by entry, not the usual way where you apply it to the spectrum, but applying it entry by entry, when does this preserve positivity? Turns out that this has quite a long history, starting more than 100 years back. So a famous result of Schur says that if you have two matrices which are positive, then their Schur product is also positive. This is the Entrywise product, which is just multiply the entries at each position. And clearly this is a real symmetric matrix. Why is it positive? Well, you can check this by just breaking it down into spectral, into the eigen decomposition using the spectral theorem. You could also generate these matrices from multivariate normal distributions, which are independent, and look at the random variable, which is the entry-wise product of the components of the random vector. So take the two random vectors, generate whose covariances are A and B, and means are 0, let's say, and now take the entry-wise product xi, yi, xy. And that's a new random vector whose covariance is exactly this matrix. So this must be positive semi-definite. So there are some very nice ways of proving the Schur product theorem. Anyway, the key point is that the consequence that was noted by Polya and Zigo, which is that if you take a positive matrix A and you apply, if you take A times A, then that is also positive by the Schur product theorem. But A times A simply has entries Aij square. So this means that if you apply x square to the entries of a positive matrix, then you get a positive matrix. So x square is one answer to this question. Now I could take B equals A times A Schur A. So then that would mean A times A times A. So x cube would be an answer, x fourth would be an answer, and by induction, every monomial preserves positivity. And also we know, of course, that if you look at the set of positive definite matrices, if you look at this condition here, then this is closed under, if this is true for A and B, then it's true for A plus B. What we just said is it is also true for A times B. And what we also understand is it's true for 5 times A, or a scalar times A where the scalar is positive. Moreover, so therefore this class of positive semi-definite matrices, i.e. satisfying this condition for all U, is closed under taking, like sums, positive linear combinations and entry-wise products. So if you want to understand which class of functions preserve positivity, that is closed under taking sums, products, and positive multiples. And so if you know that the space contains all the monomials, then it contains all the polynomials. Or if it contains 1 and x, then it contains all the polynomials with positive coefficients. And moreover, the set of positive matrices is closed. It's a closed condition to be positive semi-definite. And so if you know that it preserves polynomials, then it preserves limits of polynomials. If polynomials preserve positivity, then the limit of such a sequence would also do the same. And so if you have any convergent power series with positive coefficients or non-negative, then it preserves positivity. Yeah, so Polya Zigo noted this point and they asked, are there any other functions that work? So again, the question is, if I start with a positive matrix, I apply a function entry-wise, which functions preserve positivity? And so one answer is that every power series with positive coefficients works. Anything else? The answer turns out to be no. And this is a result of Schoenberg about 17 years later, and Rudin 17 more years later. So Schoenberg proved that there are no other continuous functions that preserve positivity for all matrices of all sizes. So the all dimensions here is crucial. And Rudin proved that you don't need to assume continuity. There are no functions other than these ones that work. Okay? So F preserves positivity for all matrices of all sizes, if and only if F is of the above form. It's a power series with positive coefficients. I keep saying positive, I mean non-negative coefficients. Okay, and such functions are said to be absolutely monotonic on the positive side. So, okay, that's a happy ending to the whole story. Let me tell you some of the strengthenings of Schoenberg's theorem. So, and they have to do with, as the slide suggests, Toeplitz and Hankel matrices. So, Rudin, as I said, Rudin proved that you don't need to assume the function is continuous. There are no other functions that preserve positivity in all dimensions when applied entry-wise. So, he was coming from harmonic analysis, and as I said, Fourier still just coefficients or positive definite sequences of positive measures on the group, on the circle group. So what this means is if you look at a positive measure, you define the Fourier coefficients for one for every integer, positive or negative, an. Then you look at the bi-infinite matrix whose I comma jth entry is a I minus j. So you have a0 on the main diagonal, a1 on the sub diagonal, a2 on the super, a minus 1 on the super diagonal, and so on. This is an infinite Toeplitz matrix. And the claim is that every principal submatrix is positive semidefinite if the measure on the circle from which you took the Fourier coefficients is positive or non-negative. Okay? So Rudin was looking at and trying to understand, if I start with such a measure, and therefore with such a sequence, by infinite sequence, I apply my function entry-wise to such a sequence. When is it that the resulting sequence I get also is the sequence of Fourier still-just coefficients of a positive measure on the circle? He was trying to understand the preservers of positive definite sequences, in other words. And he proved that this is if and only if Schoenberg's theorem. So, yeah. So what he showed is F preserves such sequences with no assumptions on continuity or smoothness or anything, if and only if F is of that kind. Moreover, it suffices to work with measures with 3-point supports. So already, if you're a power series with positive coefficients, it's easy to prove that you preserve positivity on those measure sequences. The converse is if you preserve positivity on the sequences associated to all measures, then you are a power series. But Rudin said you don't even need to work with all measures. It's a far smaller set. Positive measures on the circle with 3-point supports. Okay, that already guarantees it. So, by the way, I should point out, I mean measures which are real and symmetric around the x-axis, so that the Fourier series coefficients themselves are also real, so that the matrix you get is real, of course. So, okay. So in parallel, as I said, you can talk about moment sequences on the real line. So take a measure or a probability or otherwise, just all of whose moments exist, right? And now define the moment sequence to be just a set of moments. And then the same question that Rudin asked. When is it that you can, for which functions, if you start with a positive measure on the line, all of whose moments exist, and you act on this individual measure moments by this function, when is it that you get a moment sequence for a new positive measure on the line? That's the question of understanding moment sequence transforms. And it's exactly the same parallel question to Rudin, except now for moment sequences, you would get Hankel matrices of moment sequences rather than Toeplitz matrices. Okay, and so this is a recent result with Alex Belton, Dominic Gio, and Mihai Putinar. So let me tell you Rudin's result and then an exact parallel our result. And this works whether you look at moment sequences or Fourier sequences with mass less than rho for finite rho or all possible positive masses. So first Rudin's result, a function preserves the set of positive definite sequences if and only if it preserves the set of Toeplitz matrices of all sizes, but rank at most 3. The size of the support set of the measure governs the rank of the matrix, not the dimension. If and only if, as Schoenberg proved, this is the same as, so this is it's why it's stronger than Schoenberg's theorem. Sorry, this should just be probably -1 should be minus rho, and you assume that the measure is mass less than rho or something. Anyway, okay, so, or rather, this should just be, minus rho. Exactly the same parallel, and I highlighted the words in color that you should replace. So instead of preserving positive definite sequences, now, given a function from I to R, again, F preserves a set of moment sequences with entries in I for moments of measures on the line, if and only if F preserves positivity on the Hankel matrices of all sizes, and just like Rudin, rank at most 3. So it's the exact same parallel result, which strengthens Schoenberg's theorem because we really reduce the test set. You don't need all matrices of all sizes or all ranks, just the Hankel matrices of all sizes and very low rank 3 in any dimension. If and only if, like Schoenberg's theorem, F is exactly the same. So this shows you the robustness of this power series with positive coefficients. You try to reduce this test set in various different structured ways, and with very small test sets, you get these nice answers. Okay, so this is one thing. So these two results greatly weaken the hypotheses, as I said. One thing to note is that such matrices are precisely the Gram matrices of vectors in a 3-dimensional Hilbert space. Why? Because rank at most 3. And so the rank again governs the dimension of the Hilbert space governs the rank of the matrix, the Gram matrix, right? So what Rudin essentially showed, and now what our result also sort of shows, is if you take any real Hilbert space of dimension at least 3, that means the Gram matrices cover the matrices of rank 3 or less, and a function preserves positivity when applied entry-wise, this is the entry-wise calculus, on just all the Gram matrices in H, then F must be of that Schoenberg form or the Polyazigo form. F is a power series with non-negative coefficients. Okay? So this is a different way of saying the same thing. In fact, slightly weaker, because here I can allow for all possible positive matrices. I don't just need to look at Hankel or Toeplitz matrices. Now the point is, if you look at Gram matrices in a Hilbert space and functions that preserve positivity on them entry-wise, there is a name for this in the machine learning literature. These are called the positive semi-definite kernels on the Hilbert space. So these are kernels that are built out of the inner product, not out of the distance functions, so positive definite functions kind of thing. But these are called the positive semi-definite kernels on H. Alan Pinkus, among others, has a lot of results in this direction. And such kernels are important, as I said, in machine learning. I'm absolutely not an expert in this. So in particular, what it seems to be is that Rudin in 1959 had already classified such kernels on R3, which is relevant. As I said, in modern day, the interesting thing is at that time, there was no machine learning in 1959. There were no machines learning anything there. We were just building our first computers, but Rudin had already classified these machine learning kernels. And this is going to lead me to the next motivation. This was what Rudin came from Fourier Stieltjes coefficients, and the fact that you really need to work with very low rank matrices to make things work. That same thing now I'm going to talk about. So that was Rudin's motivation. Now let me talk about Schoenberg's motivation. And interestingly, again, this is going to come up and lead to connections again to modern day applications and statistics. Although again, at that time, I don't think Schoenberg thought about it that way. But 70 years later, now we understand that, yes, this was sort of embedded or ingrained somewhere implicit in Schoenberg's arguments. So Schoenberg was coming from not Fourier analysis like Rudin, but from metric geometry. So let's say once upon a time, shall we say? I think every story begins with once upon a time. So once upon a time, the study of positivity began with the idea of a metric space. And so this is a very old notion. Of course, it emerged from Frechet and Hausdorff and Birkhoff, and various experts worked on it, on the notion of metrics and metric spaces. Now, of course, it's studied and used all over science. So here is a sample result from Frechet, by Frechet. If X is a metric space with n plus 1 points, then it can isometrically be embedded in Euclidean space in Rn with the sup norm. I think now you can do slightly better and say Rn minus 1 or something. But anyway, yeah, this is some result. So but this is a different metric space than Euclidean space, different metric. So you can naturally ask, and people of course did, which metric space is isometrically embedded into Euclidean space? That's of course a very natural question to ask. And the same question. So Manger characterized this thing using something called, I think there's some Manger transform or the Manger matrix, I forget, something like that. Again, I haven't really studied that very well. And Frechet had a characterization as well in 1935. And in the same volume of the Annals, on the next page to Frechet, Schoenberg had a paper saying remarks on Frechet's paper titled blah, 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 where he provides a different characterization using positive semi-definite matrices. So this is a characterization. Fix a finite metric space, say n plus 1 points, x naught through xn. Then this isometrically embeds into Euclidean space if some Rm, if and only if the n by n matrix. Okay, so this m is different from n. Note. Okay, this n by n matrix, this is n plus 1, but this n by n matrix, which is the distance of x naught to xi square plus distance x naught to xj square minus dxi xj square for I and j positive. So you have n plus 1 by n plus 1 matrix. From that, you construct this n by n matrix, and this should be positive semi-definite. This is if and only. Okay, the embeddability into some Euclidean spaces if and only if this happens. It is then natural to ask, what is the m? What is the smallest possible m which will work? So, for example, if you have 3 points, if you have an equilateral triangle, right? If you have a metric space with 3 points and they're all one apart from each other, then it is clear that they can't embed into R1 because you can't build an equilateral triangle in R1. Right? Well, but it can embed in R2. So what is the smallest m such that this metric space, if embeddable into Euclidean space, embeds into Rm? Guess what? The m is precisely the rank of this matrix A. So Schoenberg provided an exact characterization, including the smallest such dimension, and this is how we connected metric geometry to matrix positivity. Okay, so Schoenberg was interested in embedding metric spaces into, of course, Euclidean space, as I said, but then further into Euclidean spheres. So, and notice here that the Euclidean sphere is of course, a metric subspace of Euclidean space. That's a different problem, which Schoenberg sort of told here, but that's not very interesting. The interesting thing here that he was concerned with was the Euclidean metric. Oh, sorry, the spherical metric. So every sphere, sorry, every sphere I claim has a rotation invariant distance. Now I mentioned this symbol Hilbert sphere S infinity. What does that mean? Well, the Euclidean space itself, R1 sits inside R2. You just attach a 0 coordinate at the end. R2 sits inside R3. You attach a 0 coordinate at the end, and so on, right? So you can keep talking about R3, R4, Rn, and so on. And that itself, you can, in principle, keep going. So what is the union of these guys? The union is infinite sequences of real numbers, but each sequence has only finitely many non-zero entries. So this is called this is some space. This is some subspace, a real subspace of R infinity, if you will. What is the closure of this under the Euclidean norm? Right? Because each subspace embeds into the next subspace with the isometric embedding. The Euclidean norm carries over, right? If you attach a 0 coordinate at the end. It turns out the closure of this is clearly, you can think about it, is clearly the set of all real sequences which are square summable. So it's just L2, little L2, the sequence space, right? Now, similarly then, what about the spheres? Well, every sphere, unit sphere in a smaller dimension, embeds by attaching 0 coordinates into a unit sphere in a bigger dimension. So what is their union? Their union is a set of all unit length vectors of finite many non-zero coordinates. What is the closure of this union? The closure is precisely what Schoenberg called the Hilbert sphere, and it is precisely the unit sphere in L2. And the set of all square summable sequences whose norm square is 1. So the claim is that every sphere, including the Hilbert sphere, has a rotation invariant distance. The idea is very simple. Take 2 points. If they are diametrically opposite on the unit sphere in S infinity or S this thing, you define the distance to be pi, the angle between them. If they are not diametrically opposite, then the 2 points together with the origin are not collinear. Therefore, there is a unique plane passing through them. You chop the sphere, slice the sphere through that plane. What you get is a great circle in R2 because it's a plane. Once you get a great circle and you have 2 points on the circle, you know the angle between them is the norm, is the distance. So again, the spherical distance is the angle distance. Okay? And that's what we have written here. That's just the arc cosine. And now what does that mean? It means if you apply cosine entrywise to any distance matrix, what do you get? You get precisely the inner product matrix between them. That's a Gram matrix, and therefore what it says is that cosine is a positive definite function. Positive definite functions, remember, are just functions on the metric space, such that, well, functions from 0 infinity to R, such that if you apply the function to any distance matrix of a metric space, entry-wise, then you get a positive semi-definite matrix. So you start with the distance matrix of a sphere, of a Euclidean sphere, apply cosine entry-wise, you get the Gram matrix, and that's positive semi-definite, as we like. So Schoenberg then classified all the functions f which were continuous such that f composed with cosine is positive definite on the infinite dimensional Hilbert sphere or on the finite dimensional sphere. And that's what this result states. It basically is the answer is that f must be a positive combination of Gegenbauer polynomials. Okay, and this is just a technical result. I'm not going to spend too much time on it. But so this is where Schoenberg assumed continuity. And this was for spheres of size R, I mean dimension R. So R-1 dimensional spheres in R-dimensional Euclidean space. Now here is the key connection to the modern day literature from spheres to correlation matrices. Any Gram matrix of vectors on the sphere is exactly the same as a correlation matrix. And the rank of the matrix is again bounded above by the dimension of the sphere, as Gram matrices usually do. Right? So f composed cosine is positive definite on a sphere if and only if f of cos of any distance matrix is positive, if and only if f of any Gram matrix is positive. But by the first bullet point, that's the same as saying if and only if f preserves positivity when applied entry-wise to correlation matrices of rank at most R. So Schoenberg's theorem is really his main theorem, not the final version, but this sphere theorem was actually talking about preserving positivity on correlation matrices by applying them entry-wise. In modern day, we call that regularization. I'll get to that in 2 minutes. But if instead now, if I did not have this rank constraint, see the size is allowed to vary, but the rank has to be less equals R. If I did not have the rank constraint, then this would classify the entry-wise preservers on all correlation matrices of all sizes and all ranks. And that is exactly what I'm going to get to in 2 minutes because of its sort of impact today in high-dimensional covariance estimation. But yes, Schoenberg did indeed make that leap. And so this is his conclusion theorem, if you will, in that same paper. So the sphere theorem in finite dimension led to the sphere theorem in infinite dimensions. F composed cosine is positive definite on the Hilbert sphere if and only if F composed cosine is a power series in cosine. But cosine being 1 to 1 between 0 to pi, or from -1, 1, cosine inverse being 1 to 1, that's the same as saying Schoenberg's original theorem. And this is where he needed the continuity. Anyway, so this is how Schoenberg came to the theorem. And as I said, okay, so there's a survey article, and we describe a lot of the motivations of what Rudin was working from, including things like Paley-Wiener theory and like work of Gelfand on non-rings and so on, all the way to what Schoenberg was working on, from Rudin and all that to Schoenberg and all this metric geometry, including work von Neumann and so on, and including, of course, conditionally negative matrices, which is what another reformulation of Schoenberg's theorem goes by. Okay, so getting back to the correlation matrix business, Schoenberg's result, though not this final version, but even this version about spheres and the Gegenbar polynomials, has attracted renewed attention because of applications again. And this is actually how I came to learn about this whole area. Is I was collaborating with Bala Rajaratnam, who's a statistician, currently at Davis. That time we were both at Stanford. And Bala was interested in this kind of entry-wise regularization of high-dimensional or ultra-high-dimensional covariance matrices. And so again, I'm not an expert, although technically I'm a B-stat, my apologies. But Bala sort of course, explained the motivation, why he was interested. And the idea comes from trying to detect structure and dependency between random variables in modern day applications. Right? So the most simple way to detect such dependency is covariance or correlation matrices. Here is a formula, which I guess we all know and probably teach undergrads. And so if you want to detect such kind of structure, then the estimation of these covariance matrices is an important and challenging problem. Challenging because unlike the statistics that I learned, and at least one other person in the audience who was my senior by 2 years, in modern day settings, the number of samples is very, very small, and the size of the problem, the dimension, the number of random variables is very large, and so the sample size is much smaller than the dimension of the covariance matrix that you're estimating. But the sample size clearly, as you can see from this formula, n is the sample size. N is an upper bound on the rank of the matrix. So we would get a highly singular sample covariance matrix, whereas we really, of course, want to work with non-singular matrices. So that's a challenge in modern day settings. And this means that if this is such a poor estimator, then you would want to sort of clean up this matrix to improve its properties, to regularize it, and so on. One concrete application, which again is very, very of very great interest to my collaborator Bala, is the theory of graphical models, which provides some connections between statistics and combinatorics. So very crudely, let me say you want to measure the temperature on the Earth. So you have a set of points where you have these temperature markers. Now in modern day settings, people even have things like 100,000 temperature markers all over the world. And this means you want to make measurements itself takes time and it's costly. To store it, to work with 100,000 by 100,000 covariance matrix is costly. But there's another point, which is that if you look at the temperature, it's say, Alaska, a point in Alaska or something, right? Then the temperature, modulo the temperature in nearby points like Russia, it would not affect the temperature in other places in the Earth. Those would be conditionally independent modulo neighbors to some other point. So it is very rare that all xj's depend strongly on one another. Many variables or pairs of variables are conditionally independent or independent, which is very helpful in the final thing that we want to do with such data and such a model, which is to predict, right? So when you have that smaller, when you reduce the dimensionality of the problem, then it's easier for predicting. And so the idea would be to leverage this independence or conditional independence structure to reduce the dimension well, what does that mean? As I think, again, we probably teach undergraduates, independence translates to zeros in the covariance matrix, conditional independence to zeros in the inverse covariance matrix, right? So how does one then sort of obtain sparse estimates? So I am giving you a sample covariance matrix. It's bound to be noisy. Every entry is going to be non-zero, or most entries are going to be non-zero. But in your model, maybe something like 90% of entries are zero because they don't depend on, those things are independent or conditionally so, or at least uncorrelated. So how do you achieve sparsity? And so one modern approach has been to use compressed sensing kind of methods, which use convex optimization, like L1, impose L1 penalties and so on. Ideally you want to impose L0 penalties to induce sparsity, but that's not convex. The point is this kind of thing works and has worked for quite a long time very satisfactorily for things like models where the dimension is 10,000 by 10,000 or 5,000 by 5,000. But if you have things like 100,000 by 100,000, then you want to do some iterative method, then that takes a lot of time and resources. And things like the climate science I told you, there are lots and lots of marker points, and this makes the problem hard if you want to use the full data. So one alternative has been recently to use the notion of thresholding, for instance. Suppose this is my true covariance matrix. I make some sample measurements and you see everything is non-zero. But these corner entries are very small compared to the others. So I make those zero. I artificially kill those entries, thinking that they are coming from zero entries in the model and it's just some noise that you're measuring. So this is natural to threshold such entries. But the point is this can be significant if you have a very large matrix and only say 1% of the true entries are non-zero. Then this really cleans up your matrix. Okay? And more generally, you can apply a function to every element of the matrix, maybe a thresholding function, maybe a power function. Like in the opening slide of this talk, apply a power function to every entry. This is a very nice procedure in the sense there is no optimization or iterative methods. This is directly applying it on the cone. So this is scalable. And the regularized matrix, whatever you get out of it, is going to be, of course, further used as a proxy for the true covariance in various procedures, which I, again, apologies, don't remember from my BStat days and haven't seen since. But so it is natural to ask, you can't just take any matrix, positive semidefinite, apply a function to every entry and expect that to work. If it is to be a proxy for the true covariance, it must itself be positive semidefinite. And so the question is, when does this procedure preserve positivity? And this is therefore critical for applications because you want to use this new cleaned up regularized matrix in further statistical procedures. And so although the heart of this question is really something, like coming from analysis, this gets used in applications. And so we come back to the same question. This is how I came to the question, thanks to Bala and our collaborations. For which functions does the function applied Entrywise preserve positivity? And now in this case, you see, we don't care about preserving positivity in all dimensions. We just care about preserving it in a fixed dimension. I know the dimension of the problem. I know how many random variables I have. So I don't need to preserve it in all dimensions, just in one given dimension. Okay? So that's the title of this slide. Schoenberg's result characterizes functions which preserve positivity in all sizes. And similar problems were studied by several people, some of whom are in the audience. But now, as I said, from applications, one is strongly motivated to study this problem in a fixed dimension. I don't just want to work with power series with positive coefficients. Those will not induce sparsity. If I apply it to a positive number, I will never get a zero. So how can I threshold or do something by applying such a function? Also, mathematically, it makes sense to ask this question. It's a very natural refinement of the of Schoenberg's theorem. We know the answer when you preserve positivity in all sizes. Now apply less constraints. What do you get? Well, what do you get? There's this very famous, well, at least for me, I keep citing this paper all the time. It's a very important paper for me, at least, paper by Harkrishan Vasudeva in the Indian Journal in 1979. And he characterized this thing for n equals 2. Which functions preserve positivity for 2 by 2 matrices? That's not too hard. The function has to be non-decreasing. The matrices have to have positive entries. The function has to be non-decreasing and fx fy bigger equals f of square root xy square. This is some kind of multiplicative convexity. Okay, n equals 1 is just that the function takes positive numbers to positive numbers, or non-negative. This is n equals 2 if and only if. How about n equals 3? And even though Schoenberg proved his theorem in 1942, this is now more than 75 years later, a complete answer is still not known for n equals 3. So the problem remains very challenging and as challenging as ever. What we have been doing recently is to revisit this problem with these modern applications, as I said, motivated by high dimensional statistics. And so here are some of the connections then. So one is to you look at you only operate on matrices with rank constraints. So positivity preservers on rank constraint matrices. This actually has been studied even by Pinkus in sort of a pure math kind of way. But for us, especially for Bala, this is important because in modern day settings, again, the sample covariance matrices that you get will be very small samples and therefore very low rank. So if I really restrict my rank to rank at most 5, which matrices preserve positivity of a fixed dimension but rank at most 5, can I get something? But also rank constraints occur in the classical literature as well. Rudin and Schoenberg both had rank constraint matrices. So you get Gegenbar polynomials from Schoenberg's result, and rank at most 3 of all sizes gives you Rudin's result already. So things like that. Similarly, you can talk about sparsity constraints, where I have some 0 patterns in my covariance, like in the opening slide, given my, say, predetermined information from the graphical model underlying the problem. Or you can talk about moment sequences or positive definite sequences, as I already mentioned. You can talk about general functions or preserving positivity, powers preserving positivity, polynomials preserving positivity. And then there are other connections to combinatorics. I will end with one of them, as well as to symmetric function identities, which I won't talk about today. Okay, so there are 2 more broad areas. One is the area of total positivity, and that's the whole area of, like it's a whole different book in itself, if you will, almost. And it has a rich history, going actually, morally speaking, back to the 1600s. And I actually gave a couple of talks this semester, the previous semester, on this in this SF seminar, Gaurav and so on. But yeah, the history of that actually morally goes back to the 1600s, but then later on it comes back to Laguerre in the 1880s, and Fekete and Polya in the early 1910s. Right? And so on, to Schoenberg, to Gantmacher and Krein, to Karlin, now of course Falat and Johnson and so on. Various people are working on that or have worked on it. And the other connection that I won't talk about is, as I said, to algebraic combinatorics and to Schur polynomials and so on. Yeah. Okay, so now let me get to the next part of the talk, which is to preserve positivity in a fixed dimension. Okay, so I continue with this problem, but now, okay, so there is one small thing that I will tell you about, which is the picture here. Polynomials preserving positivity in a fixed dimension. I'll take 1 or 2 slides on that, and then the rest of the talk will talk about powers, I think. So here is the question. Find one power series, just one, with a negative coefficient. So one of the coefficients is negative, that preserves positivity in a fixed dimension. And the point is that what Schoenberg proved is that, or what in fact Polya and Zigo proved, is that if you are a power series with all positive coefficients, then you preserve positivity in all sizes. That is literally just the Schur product theorem and basic properties of positive semidefinite matrices. So if you preserve positivity in all sizes, then as Schoenberg proved, conversely, you must be a power series with these coefficients. So if you preserve positivity in a fixed size, that's a far smaller set of conditions, constraints or assumptions. So you would expect a much larger set of matrices, functions to work. So in particular, let's say you have polynomials, well, if all the coefficients are positive, then you work in all dimensions. So if you only want to preserve it in fixed dimension, you would expect some negative coefficient polynomials to also show up. Remarkably, so Vasudeva answered the question in 2 by 2. There you can characterize or do something. But even for 3 by 3 matrices, this was not known until 5 years back, or until 4 years back. Find one power series with one negative coefficient was not known. Okay. What was known, the only necessary condition known, was by Loewner, Charles Loewner. So the condition is as follows. Let's look at a function which preserves positivity for all matrices which are of a fixed size, n by n, with entries in 0, infinity. So with positive entries. Okay, and suppose my preserver is, I know that it is also of class Cn minus 1. It's n minus 1 times continuously differentiable. Okay, if you want, you don't even need to assume that this preserves positivity on all sizes, on all matrices of size n, just on the Hankel matrices of rank at most 2. So you see, again, the rank constraint shows up. Okay, then the function, its derivative, its second derivative, and all of these necessarily have to be non-negative. So actually, this is the hypothesis here is slightly stronger. What you can say is, if you don't even assume this hypothesis, take any function, automatically this condition of preserving positivity in a fixed size would imply that the function has n minus 3 derivatives. Already that is implied. So there are some much more powerful results you can deduce from just preserving positivity. So I said, fine, let me just assume 2 more orders of derivatives are positive. Then all of those derivatives are non-negative on the entire interval. Okay. So this implies the Schoenberg-Rudin result actually. By the way, this implies it very not too hard a way for matrices with entries in I, for matrices with positive entries. Okay? That is the easier part of the Schoenberg-Rudin theorem, and that uses just Bernstein's theorem. If you have any function, all of whose derivatives are non-negative of all orders, then the function must be a power series with positive coefficients. And that's Bernstein's theorem. So if your function preserves positivity of matrices of all sizes and rank at most 2 and positive entries, then you would get that all these derivatives are positive. Therefore, by Bernstein's theorem, you are done. So that would be how you imply Schoenberg's theorem for matrices with positive entries without, So I should point out that Loewner, as I said, was a faculty at Stanford, and his PhD student was Roger Horn of Horn and Johnson. So this paper is actually by Roger Horn, but if you see the date, it's in 1969. And by then, Loewner had actually passed away already. But the point is, in his paper, Horn says that the following result is due to Loewner. And so when I was at Stanford, I actually went to the library, and Loewner, when he passed away, all his papers got bequeathed to the library. So I dug through 3 big boxes of papers, and sure enough, in one of those boxes, there's a handwritten letter or a copy of such in Loewner's handwriting, which says, when I got interested in the following question, let f be a function defined in some interval, consider all the matrices which are entry-wise positive, or with entry-wise in that interval, which properties must f have that the matrices f, a, I, j are positive semidefinite. And I found that if f is n minus 1 times differentiable, then the following conditions are necessary, that all these derivatives are non-negative. And he even explains the proof, and this is the proof that shows up in Horn's paper in 1969. The other interesting thing is that if you see there's a calculation here where there are these derivatives, there is this Vandermonde alpha I minus alpha b square, and then that's it. And Loewner calculated the n choose 2 as derivative of some determinant. And the point is, if Loewner had calculated one more higher order derivative, then he would have discovered Schur polynomials hiding in here. Interestingly, he did not, and that then turned out to be discovered in about 2 years back. That actually, if you do all these higher order derivatives than just the n choose 2 as derivative, you get Schur polynomials. And so Schur polynomials actually sit inside or are implicitly embedded inside the derivatives of some determinant applied to any smooth function or any even sufficiently differentiable function, which is a completely new connection between real analysis and symmetric function theory. But anyway, so this is a story for another day. That's a preprint I wrote in 2018. Okay. So anyway, consequence of Loewner's theorem, suppose I have something like this. Suppose I have a power series and have 2n plus 1 powers. By considering f of x, the first n coefficients must be positive. And then by considering f of 1, by this Horn-Loewner condition, and by considering f of 1 over x, or like multiplied by x to the 2n or something, so that you again make it a polynomial, but now the coefficients get reversed. The highest order term becomes the lowest order term. The lowest order term becomes the highest order term. If you reverse the polynomial, then you get that the last n, the leading n coefficients are positive. If it preserves positivity when applied entry-wise on all matrices of a fixed size, Pn. The question is, can this coefficient in the middle be negative? And more generally, which coefficient? If I give you, I have a fixed dimension, I have matrices of a fixed size, which are positive semidefinite. I act on them by some entry-wise polynomial, so which of the coefficients of that polynomial can be negative? The first n can't be, the last n can't be. That's what we are sort of saying. Can everything in the middle be negative? And that was not, of course, not known, because even a single example wasn't known. And the answer turns out to be yes. There exists a polynomial preserver of positivity on Pn, entry-wise, but with a fixed dimension, with a negative coefficient, if and only for every such negative coefficients, there are n positive coefficients occurring in lower degrees and n positive coefficients occurring in higher degrees. That's all, if and only. So you can have as many in the middle as you want, but just the first n and last n should be. And you can even do this for polynomials, you can even do this for power series. And you can do this for far more general things than power series. Sums of real powers, like Hahn series and various kind of other series. And all that is in the paper with Tao, which was recently accepted. Okay, so finally then, let me come to the last part of the talk. So positivity and combinatorics. So again, I go back to this idea of graphical models that where, used in applications or in this theoretical statistics, where it is rare for all variables to depend strongly on each other. And so many variables are conditionally independent or independent, which comes from like which comes from domain specific knowledge and applications, or from the graphical model itself in the theory. Right? And the idea is therefore that we would like to leverage such independence to reduce the dimension. And so let me set up some notation. Suppose, let's say I have a graph on 4 nodes, and you see that the 1,3 edge is missing, and so that will translate into the 0, a constraint which I'm forcing a 0 here and here in the 4x4 matrix, the 1,3 entry and the 3,1 entry. And similarly, the 2,4 is missing, so I put 2 more zeros. Okay. So the graphs for cycle, the 4 cycle, will be these kind of matrices. The matrices corresponding to the 4 cycle will be of this form, where star denotes the wildcard character, so you can put any real number there. And then, but these guys, including 0, the real number can also be 0, and otherwise you have to put zeros in all the missing edge positions. Right? So yeah, so we are encoding these dependencies via a graph where the lack of an edge signifies conditional independence or independence. So Pg of I being again a domain in R, Pg of I is a set of all matrices A in Pn, n is the number of vertices. Yeah, where Aij is 0 if I j are off diagonal and not in an edge. And notice again, I'll point out that Aij can be 0 in the starred entries. That's allowed, including the diagonal entries. Okay. But the point is, so this is all the matrices with the 0 pattern and possibly a bigger 0 pattern. PG is the positive semi-definite matrices among them. And obviously note that for any such 0 pattern, positive matrices exist because the matrices you can take are symmetric with their 0 pattern. Therefore, the eigenvalues are real. Now add a sufficiently large multiple of the identity. So that is one thing. So now I'm going to refine my problem to study preservers of positivity on these matrices for a fixed graph G. Sorry. And moreover, I will also further constrain or refine my functions. So I will not just work with arbitrary functions or polynomials or power series like above. I will work with power functions. But now the powers can be non-integer, which means my entries of my matrix should be non-negative real numbers. Okay, so suppose here is a matrix which I took at the beginning in the opening slide of this talk. Raise every entry to the alphath power for some alpha, for which alphas is the resulting matrix positive semi-definite. And this was actually studied. So apparently, Loewner was interested in this kind of a question: which powers applied entry-wise preserve positive semi-definiteness? Loewner was interested because there seems to be some connection to the Bieber-Bach conjecture. He said that, in fact, I think maybe even this slide, let me see here. The function, see, he seemed to believe that if you take any matrix, oh no, he said that these don't satisfy the conditions for all rho bigger than 1 if n bigger than 3. So for n bigger than 3, these small powers will not work. But Loewner, I think, apparently I was told by somebody, I think Johnson or maybe Horn, that Loewner believed that for all powers bigger than 1 and all matrices of all sizes, the powering up by any power bigger than 1 would preserve positivity. That turns out to be not quite true. And this is the result that is true. And this was discovered, as I said, by FitzGerald and Horn. They were both students of Loewner. And this was discovered way after they graduated. So let n bigger equals 2 be any integer, and let fx equals x to the alpha. Then this function applied entry-wise preserves positivity on n by n matrices with positive entries. Yeah, or non-negative entries, if and only if alpha is either a positive integer, that's just the Schur product here, or alpha is bigger than n minus 2. Okay? And so this can be so it's integer, every real number. This is a nice phase transition occurring at n minus 2. And this threshold, this phase transition is called the critical exponent for preserving positivity. Okay, so this is FitzGerald and Horn's result. So in particular, this is a 5 by 5 matrix. Going above, you have a 5 by 5 matrix. By the result, 5 minus 2, 3, every power bigger than 3 will work. The question is, can you do better? Can you say every power bigger than 1 will work? Is it true? I don't know if it's true. Or every power bigger than 2 will work. That kind of thing. So, and for that now, you have to leverage, you have to use the 0 patterns here. You see, there are 0 patterns in this matrix. You have to carefully use those. You have to use the graph that encodes these 0 patterns. Just a quick digression, but at the same time that FitzGerald and Horn were students at Stanford, And this is, as I said, this is about 12 years or 13 years before their paper. This was still when they were both in grad school. In the very next building to the math department is the stat department. And Sam Karlin, who was a big expert on total positivity, among many other things, was a professor there. And he had discovered the exact same threshold. This that you see 13 years after Karlin's paper here. Scam Karlin had discovered this a decade ago, before that, in via total positivity. And there's also connections to something called the Wallach set in complex geometry and to Wishart distributions or non-central Wishart distributions in probability theory. Okay, this set that I mentioned, sort of an arithmetic progression together with a half axis. But anyway, I won't get into the Wallach set part. I'll just tell you about what Karlin discovered. So Karlin was looking at this Polya frequency function, whatever that means. It's a one-sided function. It is 0 until the origin, and then x times e power minus x. Okay? And so that decays again to 0. And what Karlin showed is that if n is an integer, then this the nth power of this function has the following property. This for all matrices, you take n scalars x1, x2, xn, n scalars y1, y2, yn, and look at omega of x1 minus y1, omega of x1 minus y2, and so on. Then for all sizes, the nth and all integers, this matrix has non-negative determinant. Okay. And now what he said is, what happens, just like what I was talking about in the previous slide, what if you take non-integer powers? This is like a Schur product theorem kind of thing. Every integer power works. What about the non-integer powers? It turns out they are never going to preserve positivity on matrices of all sizes, but they can preserve positivity on matrices of a size up to a certain point. And guess what? The same kind of power set works. Let alpha be a power which is either an integer, which works on matrices of all sizes for even that kernel, or an integer, a real number above n minus 2. Then if you take that same function, Karlin's function, omega of x, raise it to the alpha power, and you look at k different arguments, as long as k is capital N or less, this will work. You get that the nth power is also totally non-negative, or the determinant is all non-negative. The question therefore remains, what about negative powers can be easily discounted? So the question remains, what about non-integer powers less than capital N minus 2? And somehow, remarkably, this did not seem to be written in literature. So earlier last summer, just a few months ago, I was able to answer that yes, this will not work. You can find some n by n matrix. You have to find n arguments in x and n arguments in y, such that the determinant, so that the submatrix is not totally non-negative. It has a negative determinant, negative submatrix determinant. And a key ingredient in this proof that I provided were some results in 2020 and even in 2017 by Tanvi Jain, who was in the audience. And somehow, maybe my belief is somehow until Tanvi's paper and methods came along, it wasn't ready to be adapted to answer Karlin's question. Once it did, then Karlin's question could get answered. Anyway, so yeah, that's the two sort of very related and closely knit papers of Tanvi that helped prove this, answer this converse to Karlin's question. And similarly, a converse to Schoenberg's question in some annals paper in 1955, again, crucially using her results. Okay, so back to now the problem at hand that I started with. Can we improve on the set of powers, preserving positivity, which by FitzGerald and Horn's theorem was just positive integers and everything above 3. But now can you do this for a specific matrix with a given pattern of zeros? And the idea is to exploit this sparsity structure, the zero pattern. So more generally then the same question, can you, given a graph G, let's say, can you compute the set of powers preserving positivity on PG, all positive matrices with zeros according to G? And if suppose G has n vertices, then by FitzGerald and Horn's theorem, every n by n matrix and every power above n minus 2 will work if the matrix was positive, right? To preserve positive. So in particular, if the graph G has n vertices, then every power above n minus 2 will also lie in this set, HG. Which means there is already a smallest number above which every power lies in HG. And let's call that number the critical exponent of G, of the graph G. So the natural question is, how does the critical exponent and even maybe the bigger set of powers themselves depend on the structure, the combinatorics of the graph itself, on the structure of G. Does it depend on the structure of G? How does one make it work? So by FitzGerald and Horn, as I said, this number always exists. It's less equal to the number of vertices minus 2. FitzGerald and Horn studied the case where the graph is complete. What does it mean for the graph to be complete? What is PG? Well, remember, PG had a constraint fixed 0 if and only if there was no edge there. If the graph is complete, then there are no missing edges. So there are no constraint zeros. So the full set, Pn or PR. And then he showed that the critical exponent is R minus 2. In our paper with Dominique and Bala in 2016, we studied the case of trees where we showed that the critical exponent of any tree for any size is 1. Okay. So, sorry, yeah. So now, but this graph is neither a complete graph nor a tree. So can one compute the critical exponent for a family of graphs that contains this graph, that contains complete graphs, that contains trees? The answer turns out to be yes, of course. And the idea is, as in the title, chordal graphs. So trees have no cycles of length n bigger equals 3. A graph is said to be chordal if it has no induced cycles of length bigger equals 4. So this graph on the right is not a chordal graph because you see there's a cycle. And the idea is whenever there's a cycle, you have to put a chord through it, like we did to get this graph. Then it becomes chordal. Sorry. So let okay, so here is my final result and the main result of this paper in 2016, again with Dominique and Bala. The idea is we will compute the critical exponent of every chordal graph. So remember, here are 2 chordal graphs for which we knew the critical exponent. The complete graph had critical exponent r minus 2. So all powers above r minus 2 work and only the integer powers below r minus 2 work. For every tree, all powers above 1 work. No non-integer power below 1 works. Okay, so now for chordal graphs, here is the answer. First, let us define something. Sorry. Let KR1 be the almost complete graph. Almost complete means take the complete graph and remove one edge. Okay. Let R of G, so now given any graph G, let R of G be the largest integer such that either the complete graph or the almost complete graph of size R of G is an induced subgraph of G. In other words, just the almost complete graph is a subgraph of G, induced or otherwise. Okay. R of G is, so this is clearly just, there is no analysis here. There are no matrices here. This is a constant given the graph. It's completely combinatorial. Here is the main theorem. If G is any chordal graph with at least 2 vertices, connected or otherwise, then the set of powers preserving positivity on positive matrices is the positive integers, that's just for the Schur product theorem, and r minus 2 comma infinities. Again, integer, integer, integer. When you reach r of G minus 2, you take every real number beyond that. So for example, for complete graphs, of course, the largest complete graph sitting inside is the full graph, so r minus 2. For a tree, the largest complete graph sitting inside a tree, you don't have triangles, you don't have cycles, so that is just K2. So n union 2 minus 2 comma infinity. But that's not true because the largest almost complete graph in a tree of at least 3 vertices is a 3 path. But a 3 path is exactly the almost complete graph on 3 nodes. And so you get 3 minus 2. So you get 3 minus 2, which is 1, and 1 comma infinity is exactly the answer. And so this result on chordal graphs unites a lot of different families. It unites complete graphs and trees, also almost complete graphs, also band graphs, split graphs, Apollonian graphs, and several such. Interval graphs, I think, as well. For all of these graphs, one can compute the critical exponent. And again, I want to point out that you see the critical exponent is defined using matrix positivity and Entrywise powers and so on. Yeah. The condition here, the R of G condition here is completely combinatorial. It doesn't depend on any matrix. It just depends on the graph. And these turn out to be equal. Okay. So again, now given the previous example, the working example in the beginning, all powers above bigger equals 2 work, because for this banded graph, you can do the combinatorics and you can check that the critical exponent for any banded graph is of this kind. And so that's why this works. So now indeed we can improve on the previous, on the critical exponent we started with 3 or above to 2 or above. Okay? And then there are all kinds of questions you can ask, which I don't know the answer to, but they are all open. Is the critical exponent of any graph always an integer? In fact, is the critical exponent of any graph of this kind, the same R of G, the same combinatorial rule? And so all these answers would be very nice to have. We asked experts, oh, is the critical exponent defined in this way? Yeah. At least connected to other combinatorics, the traditional combinatorics, if you will, coming from algebra or combinatorics, not coming from matrix positivity. And I have asked this to lots of experts, and so far at least nothing is done. The largest R for which the almost complete graph is a subgraph. Can this be written in terms of the chromatic number or some independence number or a combination of these? And nothing is done. Okay. So yeah. So thanks are due to various people and agencies and so on. And these are the references. So this is where we improved on the Loewner-Horn theorem to remove the continuity hypothesis. This one is where we computed the critical exponent for a tree, and this one where we computed the critical exponent for every chordal graph. This paper with Mihai and the paper with Tao were about polynomials acting entry-wise, preserving positivity in a fixed dimension, and having a negative coefficient, 4 and 7. Paper 6 is the survey. Paper 5 is this parallel condition to Rudin's result about using only toplets rank at most 3 matrices to preserve positivity in matrices of all sizes. We use Hankel in the reference 5. And I'll end by mentioning that all of this, most of it at least, all of this will go into a book that I'm writing, which is about to come out both with Cambridge University Press outside India and with the TRIM series inside India, Professor Bhatia at least. And the sort of a bigger set of notes, including the notes about Polya frequency sequences, Polya frequency functions, root location results like Mallo's theorem and Schur composition theorem and so on. All of these things are available on my website in my lecture notes. Okay, that's it. Thank you again.
Thanks, Apoorva. Anyone wants to ask any question or have any comment? You can unmute yourself and ask.
May I ask Sophie here from Srinagar?
Yeah, sure.
You have two simple things. One is a comment, and the other is a small question. The comment is that, I mean, when you talked about Schoenberg's theorem in the beginning, involving the isometric embedding of a finite set into an Euclidean space, then the dimension of the target space is equal to the rank of that positive different matrix, right?
Sorry, here? Yeah.
So that is the rank. So the point is, I mean, my comment is that if you wish to settle for an isometric, or an almost isometry, rather than an isometry, then you can drastically reduce the dimension of the target space. I mean, that is a consequence of the so-called Johnson-Lindenstrauss reduction lemma. So you can reduce it and reduce it in an appreciable way if you just settle for an almost isometry, where the distances are almost preserved, I mean, within an epsilon. So is it okay?
I think he's lost his connection.
No, I am very much there.
No, Apoorva.
Okay.
Yeah, now he's here.
Yeah.
I think I went offline. My apologies. I don't know why. I'm in my office. Sorry. So do you mean by Lipschitz embeddings?
Better than by Lipschitz. Yeah. I mean, it's an epsilon perturbation of an isometry.
Oh, okay. And then you can drastically reduce. Is there like so what would be the bound like if it's n points in the metric space?
Well, I mean, there's an estimate on this on the number of points and that epsilon that you choose to begin with.
Okay.
And
dimension is a function of n and epsilon. Okay.
Right. And the next is maybe a trivial question. You see, when you talked about the rotation invariant Manger on the infinite dimensional Euclidean sphere,
yes.
Can you realize it in terms of the rotation invariant measures on the finite dimensional these spheres, Euclidean spheres?
Yes, because if you take any 2 points, If you take any 2 points on the Hilbert sphere, then they together with the origin will lie on a unique two-dimensional plane.
Okay.
And therefore, yeah, you actually realize it as something in R2 itself, S1 in R2.
Yeah. S1, right. Okay.
So this yeah.
Right. So, okay. Well, that's simple. Okay, thank you.
Yeah, it's just literally, that's why it's the arc length along a great circle, which means it is all in S1. Yeah.
Thanks.
Yeah.
So anyone who wants to ask a question?
Hi, Apu, this is Dipan. Can you hear me?
Yes.
So, very nice talk. Thanks. So, just going back to your statistics connection. So that
You are free to
question,
correct me as much as you want.
no, I don't know much about this anyway. So, but the main question seemed to remain unresolved. At least, maybe I didn't understand. So, when you do this thresholding in a variance covariance matrix or a correlation matrix, does that retain? I mean, can you answer
So
when it will retain
that's
threshold?
right. That's a good question. I know one result at least, that somehow slightly negative result. So let me look at matrices with a given graph structure, like in the end, PG. So what Bala proved with my collaborator Dominic, I was not involved in this, was that thresholding at some level, so retains positivity in PG, if and only if thresholding at every level retains positivity in PG, but if and only if G is a tree. So for very, very sparse matrices, this does happen. Otherwise, you have to look at it sort of more, I guess, case by case for individual matrices. But in a principal way, you won't get it. The other thing that Manjunath over here is trying to do is somehow, he's asked at least one of his students this question is, okay, thresholding, let's look at the power function, let's say, but it can be asked about any function. So if you look at the power function, let's say you only look at the correlation matrices. So the set of correlation matrices has a finite volume because it's sitting inside a closed and bounded set, finite measure. Right? So if you say figure out some kind of a probability distribution to put on the set of space of correlation matrices, or maybe even on the set of all positive semi-definite matrices of a given dimension. Now, if I fix a power which is less than the critical exponent and which is not an integer, then of course we know there are matrices which will not be preserved. Right? And therefore, if there are such matrices, then clearly not being preserved is sort of an open condition. So, around each matrix, you'll find a small open neighborhood so that it's not preserved. So, what is the probability that if I take a generic, if I draw a positive semi-definite matrix from this distribution on Pn for a fixed n, and I apply this a given power Entrywise, what is the probability that the resulting matrix will be positive semi-definite? And it seems to him, he told me that it seems that the probability tends to be quite large. So the bad set where this doesn't happen shrinks in volume, or asymptotically, as I think he said as n goes to infinity, regardless of the power you use, the probability starts going to 1. So the bad set sort of keeps shrinking to 0, which would be interesting to prove somehow, but I don't think he has written it up or his student has written it up.
Okay,
So
thanks.
there are some things, yeah. So for thresholding, the answer for at least the partial result I have for specific graphs, the only graph for which it works always for any level and for even a single level is the tree. And in general for n by n matrices, powering up will generically work as the dimension grows larger. But you can in principle ask the same kind of question for thresholding. And I don't think people have looked at that either. So maybe it's worth simulating and understanding. Are all these things generically true, and all the things that I'm dealing with only sort of some pathological low probability cases, if not 0, but at least very low? I don't know.
Okay, thanks.
Anyone else? So Apoorva, we have a few comments on appreciations on the chat.
Oh,
So Professor Ajit Iqbal Singh, Professor Pratulananda Das, and Professor Sophie, they liked your talk. It was a beautiful talk, and
thank you.
yeah, there's
Very, very honored.
yeah.
Very kind. But it's a nice subject. It connects to lots of different areas, which is what I
Yes,
really like.
that's true. And every area has basically it's interesting to see. In
Yeah,
every area, it's interesting. The
in
problem.
every area, a bunch of areas of history, bunch of areas of modern connections. Overall, it's very nice.
That's true. And the presentation was excellent. So, in fact, everybody could understand more or less. I think you connected very well. And
Thanks.
Please have a coffee on our behalf.
Coffee. Yeah, I don't know. Yeah, I know. This is
On our behalf, that is.
I would say you can have the coffee. Deepayan knows this for 20 years. I don't take tea or coffee. So.
Okay, have a better drink then. Yeah.
That I'll take you up on it when the pandemic goes away.
As of now, digital coffee.
Digital coffee. Well, we can have digital cookies.
Yeah.
Deepayan knows more about digital cookies than I do. But, yeah.
Okay, thank you.
Thank you.
I just put in the chat, he could put so many areas together in one big space because they formed a positive definite matrix.
That way. I wasn't sure what your... Well, first of all, you didn't have a space bar, so you wrote Putin. And I wasn't even sure what Putin has to do with this.
Okay, all the
With a capital P. I think maybe, was it autocorrect? I don't know why there's a capital P. But yeah, no, it's very, all the connections are very fascinating to me.
Yeah, nice talk. Yeah, well, actually, it's nice to see all connections, though I couldn't follow some of the things, but
no.
quite interesting.
This is not, I mean, yeah, I think it also must have gone a little fast also. It's not.
Okay,
I tried to pack maybe too many things also in one talk, but all of these connections are worth talking about it. And then I couldn't even mention Fourier frequency sequences or functions.
When exactly do you think the book is going to be out?
The book, I'm actually proofreading my own book right now. So I printed out like the whole book on paper, and I'm going through it carefully. And this is the final push. So hopefully by the end of this month, I hope it will be out. The larger set of lecture notes but then that sort of mixes positivity and total positivity. So it's not keeping the two themes cleanly separate. Is already on my website. That's a huge set of lecture notes. But again, I've tried to keep everything self-contained, like modulo one course in linear algebra, one course in calculus. And that's all you should need. And I've tried to put in as much history as I could find, as many connections to Fekete and Descartes, as I said, Laguerre. One interesting connection I learned, which maybe people who have taught calculus to undergraduates might appreciate, is I was looking at positive definite functions, as I said, and I was looking at, so to do my research, I looked at all these literature, and there was a big survey, a very nice survey with all the history from Buchner and Schoenberg and all the, even before that, by somebody called James Drury Stewart. And I had no idea who this person was. I eventually Googled, it turned out he was in McMaster in Canada, and that's where he passed away. And he did his PhD under somebody he did his master's in Stanford and his PhD in Canada or something like that. And eventually, after digging around, I found out this is the same Stewart who has written all those calculus books, Calculus Early Transcendentals by Stewart and Calculus First Edition by Stewart. That is the same Stewart. So before he started writing calculus books and built a huge fortune in royalties and built a huge house from those royalties in the shape of a violin, which is on the cover of most of his books. Before he was doing calculus writing, he was studying positivity and positive definite functions.
No, are you referring to Ian Stewart?
No, J.D. Stewart.
J.D.
James Stewart is the author of that survey on positive definite functions and of all these calculus textbooks, out of which I have myself taught calculus in many undergraduate.
Is that the paper in Rocky Mountain Journal?
That's exactly the paper in Rocky Mountain Journal. Yeah, exactly. So it's a very, very nice survey. It's a wonderful survey. One of my co-authors was jokingly remarking, he should have stuck to positivity, not written calculus textbooks. But yeah, he did his PhD as well on positive definite functions. So There are all kinds of interesting connections you find when you go digging for history. But yeah, the book should be out at the end of this month. It will be submitted to the publishers, and then it depends on the publishers. I don't know how much more editing they do. But I have been in touch with, actually, I'll tell Professor Bhatti, I've been in touch with both the Jain brothers, and they told me a bunch of things to look for in the margins and the things when I write for trim. So I will do that as well.
So thanks, Apoorva. And very nice to hear you.
Yeah, it was nice to see you as well. I know I have wanted to talk to you for quite a while about that paper and the kernel, the Jain Karlin Schoenberg kernel.
Yes, I also looked at it, and I was In fact, recently I looked at it at the end of the year.
Well, if you can solve it,
I've now. That I'm not sure.
It's such a simple function, but so tricky because of the max. I just have no intuition myself, but
exactly. So one will have to.
We'll see. It may take some time, but hopefully, we'll see.
Yeah.
When the pandemic goes away, maybe I'll come over and we can talk.
That would be great.